Nikos, we don't hear you.
Okay, now you should hear me. Yes, thank you, and sorry for that. So I will repeat myself. Welcome to everyone. Welcome to the speakers, and welcome to the attendees of this webinar. It's CEMBUREAU's webinar about secondary materials, and my name is Nikos Nikolakakos, and I am Environmental and Resources Manager at CEMBUREAU. I will be moderating this event, presenting the speakers, and go forward. So I will make a short introduction to the topic and then present some practical details. First of all, this topic is about the secondary materials. Everything starts from the Green Deal and the European Union and the commitments and the vision of the European Union to become the first carbon neutral region in the world. So some years ago, the European Commission published the European Green Deal, and as answer, CEMBUREAU, the European Cement Association, published its own Carbon Neutrality Roadmap, what will be the ways to reach the zero CO2 emissions from the cement production in 2050, with an intermediate step in 2030, analyzing the whole value chain, the so-called 5C approach, from clinker production, cement production, concrete, and then construction and carbonation. And one part of this 5C approach, of this pathway, is the use of secondary materials. For this, CEMBUREAU assigned ECRA, the European Cement Research Academy, to prepare a study, which will be one of the presentation of today, the first one. Today we will have speakers from both industry and academia, kind of divided panel, two people from the industry and two people from the academia. And the conclusions will be made by Rob van der Meer, our Industrial Policy Director at CEMBUREAU. A few practical points before going forward to the webinar. So we have around more than 500 registrations to the webinar. So a lot of people attending. The webinar will be recorded, and the recording will be shared after the session with all the people who have registered. We will make a pause during the presentation by Holcim, as the company asked us not to share the presentation and the recording, and we will respect that. But all the other presentations and the recording will be shared with the registration people. As CEMBUREAU, we follow the competition law guidelines. So during this webinar, we will not be mentioning prices of the products or market shares. And finally, I would like to invite you, the attendees, to pose questions during the sessions, for the speakers. We would like to preferably to use the Q&A, function of Zoom. It's much easier for the speakers to reply there. We will try to answer the questions live, but at the same time, we need to respect the timing to limit the whole webinar in 2 hours. So we have decided to have 25 minutes per each speaker. So if not possible to answer the question live, I would kindly ask the speaker to write the answer in the Q&A. It's a function that works well in Zoom. So you are very welcome to post your questions in the Q&A, and the speakers could answer there. And before going to the first speaker, a quick mention to our publications. So on our CEMBUREAU's website is published today the ECRA study about the alternative raw materials. And together with this study, we have prepared two supplementary documents, one communication leaflet, a 3-page leaflet with some nice infographics and messages, together with a Q&A document, a more detailed document with technical information for people who want to look the topic further into more deep. So all these three documents are available on CEMBUREAU's website. And in the coming days, there will be publications on our social media accounts on LinkedIn and Twitter. So you are very welcome to follow CEMBUREAU's account on the social media to stay informed for the new publications. So that will be all from my side as an introduction. I would now invite the first speaker, Volker Hoenig, who is the Managing Director of BDZ, the German Cement Association, with more than 30 years of experience in the cement sector, a very good expertise in the thermal processing, energy efficiency, fuel and raw material substitution, fuel optimization, and many other points. So Volker, thank you very much for your availability to the webinar, and I will pass the floor to you to share your screen and start the webinar with your presentation.
Yeah, thank you very much, Nikos. So I will share my screen.
Yes, it's perfect.
So now you should see the full screen, right?
Yes, it's very good. Thank you.
Okay, yeah. First of all, hello to everybody. What is a very interesting webinar on this topic of alternative raw materials. As Nikos said, we have, as VDZ, but in the name of ECRA, the European Cement Research Academy, a study in 2021 and 2022 about the status and the prospect of alternative raw materials in the use in the European cement industry. And I'm happy to present a short summary, I must say, because the full presentation which we prepared is much long for today. So it will be a short summary and with let's say one good example for one European country and the European level. The objective, as Nikos said already, was a kind of positioning of the use of alternative raw materials, or ARM as we call them here, in the three parts of construction: clinker, cement, and concrete production, before the background of circular economy, first, and second, decarbonization. So what we did is, first of all, we looked on the current status, mainly based on statistical data which are available at CEMBUREAU, but also other statistics, especially for concrete production. Then we assessed the future potential of the different materials used. We analyzed the waste management system and the recycling recovery targets of a number of countries. I will come to that. Then we looked at the contribution of ARM use to the country's circular economy and to CO2 emissions reduction of the cement sector in the given countries. Last but not least, we had a look at barriers and drivers on different levels: legal, social, and also technical. In order to limit the efforts to some extent, we focused our study on 7 what we called key countries: Austria, France, Germany, Italy, Poland, Spain, and UK. And we looked at the European Union as a whole. I have 2 slides about the methodology which we use, because the methodology, of course, has an important impact on the results. First of all, as I said, we looked at the amounts of consumed alternative raw materials and the current substitution rates. We looked at the differentiation of ARM types within the different countries, because this is very different from country to country, as we learned. And we did this, besides the available statistics, also by interviews with the respective national cement associations and also members from cement companies working in those countries. In order to improve our assessment regarding future prospects, we analyzed the situation as well as the future, let's say, expectations of those industry sectors from which the cement industry receives significant amounts of materials, like the steel industry, like power generation, and so on. And we also developed what we called fact sheets about important materials. I will not have the time to go on this fact sheets in detail today, but they are available as well. And we did the analysis of the sector-specific roadmaps for the future developments also on European level, and where available also on country level. Regarding technical and environmental aspects, we looked on impacts of the ARM use on emissions, CO2, trace elements, organics, on the products, mainly heavy metals, trace elements, and on the assessment of technical measures which would allow or will allow higher ARM use in the future, like, for example, advanced emissions abatement when we talk about organics, for example, or also pre-treatment of certain materials or byproducts which could be made available in the future for the industry. On European level, one important aspect was, of course, the contribution of ARM use to CO2 reduction or avoidance, and chances and limitations of the future potential of the materials which are used already today regarding the development, and possible new materials which may be used in the future, but which are not yet used today. Important was to, let's say, to define what we mean with alternative raw materials, because we have seen that the definition also in the available statistics is not the same in all countries. So we have said that ARM are defined as materials which are wastes or byproducts from other mainly industrial processes or societal sectors, and which are not classified as alternative fuels. So we know that we have materials which are somewhere in between fuels and raw materials, like, for example, sewage sludge and these things. So this was our differentiation here. We have looked at ARM, which are used in clinker, cement, and concrete production. And we have excluded all materials which derive directly from the cement production itself. So we didn't include, for example, bypass dust, CKD, used refractories from the kiln, and so on, and materials which originate from natural sources. So we didn't include natural puzzolana or calcined clays. Okay, as I will only have the time to present one country today, and together with CEMBUREAU, we have selected Austria because Austria is a very good example with a country with a very well-developed waste market for the industry, and this is why I will focus a bit more on Austria today. I will start with clinker production, so the use of ARM in clinker production. Do you see my mouse?
Yes, we can.
Okay, so the current situation is characterized by, and we used 2019 as a reference year because those were the latest data which are available. About 800,000 tons of alternative raw materials have been used in clinker production in the Austrian cement plants, which corresponds to 15% of the total raw materials which are used for clinker production there. This is, I can say this directly, this is the top level in Europe. And when we look which kind of materials these were, we see in the table here, these are the top 10 materials, that in Austria there is a certain focus on waste from construction. So waste ceramics, tiles, and other construction products. And on the same level, spent bricks. This is very typical for Austria and also very specific for Austria. Then we have other materials which we also find on a more or less high level in other countries, like fly ashes, for example, used foundry sand or bottom ashes. So which totally make up about 800,000 tons. We will see also later in a picture that the trend of the last years has been growing. So the Austrian cement industry was very successful also to increase over the time the use of these materials in clinker production. From the interviews with the Austrian experts, we derived that they expect that also in the future, these main two types, ceramics, bricks, and spent bricks and tiles, will also increase in the future. While on the other hand, and we will hear this more often during this presentation, the fly ashes will shrink considerably due to decreasing power generation by coal-fired power stations. Another expectation, which is also specific for Austria, is that the experts expect that higher alternative raw materials quantities will be imported from abroad. Coming to the level of cement production, we see here in this slide here, cement production was about 4.3 or 4.4 million in 2013, and it increased to about 5.2 million tons in 2018-2019. And we can see that the level of ARM used in cement production was about 1.1 million in 2018 and 2019. When we have a deeper look in the different kind of materials, we see here that the main 3/4 was blast furnace slag. I mean, we know that Austria also has a strong steel industry today, and the blast furnace slag is mainly used in cement production. Furthermore, flue gas desulfurization gypsum has been used, and also some fly ashes as materials in cement production. Also here, when we look at the future expectations, it is expected that fly ash will and slag will decrease mid to long term. And you can imagine that slag being representing 75% of these materials, this would mean that the total quantities of ARM would decrease significantly. But on the other hand, there is a development which did not start really yet, because there are still research ongoing, that other mineral components will gain more importance in the future, especially with regard to concrete fines. And then the third level is concrete production. I must stress that the statistics for let's say the use of materials in concrete production is not as good as the data for clinker and cement production. So what we gained were these results here. So we see first of all the ARM used in concrete production as percentage here. In blue, we have Austria, and in gray, we have EU28. First of all, we see that the level as such is much, much lower, with about 2 to 3%. And what we see is that the level, that the trend has been negative over the last 7 years. And the most used materials, it was not possible to get a full information on the used materials, but at least the most used ones, and this was fly ash, at least 2018 to 2020. So fly ash from coal-fired power generation went mostly in concrete production. The level of ARM content in concrete was about 50 kilogram per cubic meter, coming down from more than 60, around 67 to 50. So corresponding to only more or less 2% today. yeah, having this decreasing trend in mind already, it is clear that when coal-fired power generation will decrease or even stopped in the future, also the fly ash will not be available anymore, at least from Austrian power generation. And the expectation is that especially materials produced from recycled concrete, kind of as used as aggregates, will play an increasingly important role in the future. Now the very interesting question, what is the level of CO2 avoidance with the use of alternative raw materials? And we have looked here mainly on the level of clinker production. It is not so easy to do this estimate or to do this calculation. So we have had to look for some assumptions, and there's also quite a big uncertainty in these estimates. So we did this based on the calcium oxide content, so the decarbonated calcium oxide content in the materials. And you can see here the different materials from which we have assumed that they are decarbonated because they come already from a high temperature process. And then we have done some estimates on the composition, and going just to the mean estimate, we have come up to about 35,000 tons of CO2 per year, which have been avoided by the use of these materials. And this corresponds to about 10 kilogram CO2 per ton of clinker. Having in mind that producing clinker makes up about 800 kilogram or 850 kilogram of CO2 per ton of clinker. Summary for Austria. From the market point of view, we can say that Austria has a really well-developed alternative raw materials market, which allows this really high level of 15% substitution rate in raw materials. And by this, Austria is number one in Europe. You see here again this positive trend, which I've mentioned already before. So in 2013, the level was 13%, and in the meantime, it came up to 15%. The market, the waste market, is characterized by a quite large variety, so very different raw materials which are used, which of course allows the cement producers a quite high flexibility. With respect to the specific situation in the cement plants, and also with respect to the raw material composition they have on site. Regarding the political environment, we have also a very nice green here. So from the experts, we heard that no real barriers have been identified on the political level. So from political side, the use of ARM is seen is positive in the sense of waste market and use of materials from one sector in the other sector. We have two yellows here, which is on one hand side the societal perspective. So the public acceptance is not everywhere perfect, but it's okay. It has been assessed as medium. So there is some negative attitude in the society with regard to the use of alternative raw materials. And regarding the industry itself, we also have a medium assessment here because for further increase of use of alternative raw material, additional capex is needed in the cement plants. First of all, for additional dosing, handling, storing, and so on. Also, licensing is an issue, of course. First of all, it takes time. Second, it costs money. Another point in Austria is that the cement plants in Austria have already invested in some of the plants have invested in advanced emissions abatement techniques, which allows them already today to use, for example, also materials with higher organic compounds. So they have invested in, for example, RTO in order to burn organics in the raw materials. All in all, we can see here that in clinker and cement production, nearly 2 million tons of ARM have been used in order to produce 5 million tons of cement, so which is really, really a lot. Now I would like to compare this with EU 28.
Sorry, just to highlight that there is four more minutes to finish the slide and to have some questions. Sorry for that.
Yes, I have 3 more slides.
Okay.
So on the European level, we see here we have on the level of clinker production, we are on a level of between 3 and 4% today, compared to the 10% with clinker for Austria. On European level, we have also seen huge differences between the different member states regarding market situation and also regarding the implementation of the EU landfilling directive. Some member states have really low landfill taxes for mineral wastes, which reduces or decreases the availability of such materials for the industry in those countries. This is also why we have assessed here the political environment in red, so high impact. One other interesting point for some European member states is that there are legal barriers regarding the reuse of landfill materials. So, for example, there are countries like Poland, they have huge landfills from the past, or for example, fly ashes from power generation, and it is not possible today, maybe in the future, to reuse these, to open up these landfills again and reuse those materials due to legal barriers. But this is, of course, nevertheless, a huge potential for the future. And with respect to time, I go then to this next slide, which I think is very important. It gives an assessment of CO2 avoidance by decarbonated raw materials on European level. When we go directly to the graph here, we see here Austria with a 10 kilogram of CO2 avoided per ton of clinker by alternative raw materials. We see that also Poland is quite high, but the average is on a level of 3 kilogram per ton of clinker. If the European cement industry would like or wants to fulfill the targets from the CEMBUREAU roadmap, these numbers would have to go up from 3 to 45 kilogram per ton of clinker. So this is really a huge increase, which would be needed in the future. And summarized, when we look at the availability of decarbonated materials, we have assessed this as really, really challenging to achieve. Come to the summary. The use of alternative raw materials differs significantly between the different countries. The availability of some traditional ARM will decrease significantly in the future, like fly ash, blast furnace slag. But as I mentioned, in some member states, historic landfills could be recovered and be made available for cement and concrete production. Furthermore, some new ARM have to be made available for the cement and concrete industry, like, for example, ashes from sewage sludge incineration, bottom ashes from incineration, slags from steel production with direct reduction in the future, and maybe others. And construction and demolition wastes also offer big quantities, but their use in clinker production is limited by their composition. For example, concrete fines are rich in silica which has to be compensated in clinker raw meal with high quality limestone. And the use of concrete waste as recycled aggregates in concrete is the biggest opportunity. Regarding limitation, as I said, the low calcium content in most ARM limits their use in clinker to a few percent. Some materials will have to be treated to make them suitable for cement and concrete, for example, in elimination of high heavy metal contents, like in incinerator slags, for example. The content of organic matter limits the use of ARM in the raw mill. Such materials can only be used in the hot kiln section or in plants equipped with RTO technology. And last but not least, the impact on CO2 emissions is limited. So today we have about 0.4 million tons of CO2 per year, which are abated by these, but the availability of these materials is rather limited. So as I mentioned already, to achieve this 8% target from the CEMBUREAU roadmap with this mean is really challenging. Thank you very much, and I'm open for questions.
Thank you very much, Volker. Thank you very much for the excellent presentation. And there are several questions on the Q&A session. I have to say that some of them are already answered by Rob van der Meer or also some other participants. So we really welcome this lively exchange, and we're really looking forward to interaction during this webinar. I will focus on one or two questions that are still not open. And if you like, after Volker, you can try to complement the answers already replied. So a question by Claudio Mazzari. What about bottom and fly ashes from waste to energy plants? If you like to give a short feedback.
Yes, these materials are quite high in heavy metals, which is the reason that at least until today, these materials are not so much used in the cement industry. We know that there are some countries where permits have been given to cement plants to use them. In Germany, we ourselves have a research project on this topic. So for us, these kind of slags are a good example where materials should be treated in the future in order to make them available for the cement industry also in bigger quantities. But as I said, they are low in calcium use usually and high in silica, which limits their use in clinker production.
Okay, thank you very much, Volker. There are many interesting questions, but in terms of the timing, I would just take one more and then go to the next speaker. So from Rita Braids, for countries that don't have steel industry or coal for electricity for fly ashes, what ARM should we use? If there can give a suggestion, different type of ARM.
I mean, in our study, we have assessed most of them, but I mean, there are quite a lot of materials which are also used already in cement production. For example, as silica component, we have the foundry sand. As a calcium component, very interesting are, for example, lime wastes, lime sludges, and so on. The problem is that those materials are limited in quantities. And compared to the huge quantities of raw materials which are needed in clinker production, the availability is really limited. In cement production, I don't see so many other materials from the waste and byproduct side. So we expect that, for example, calcine clays will play an important, bigger role in the future. Also, limestone itself will play a more important role in future cements, clinker-efficient cements. Yeah, but these are then not alternative raw materials as we have them defined here.
Exactly, yes. This was another question earlier before about the scope of the study and the calcined clay or limestone. We will, in order to go to the next speakers, we will close here. And if you like, Volker, we can continue the exchange in the Q&A. So thank you very much for both the study and the presentation. And now we will go to Daniel and Sinan to the next presentation. So Daniel currently is a professor in the Technical University of Darmstadt in Germany, but she has 19 years of working at the University of Luxembourg, and where she specialized in the sustainable concrete structures. And Sinan Kasamani is a doctoral research in the University of Luxembourg. So Daniel and Sinan will present the next topic. I think the floor is first to you, Daniel, and then to Sinan.
So many thanks for your kind introduction. Sinan will now share our presentation. Yes, many thanks. So I will now present to you a project that we did still at the University of Luxembourg when I was professor for solid structures at the University of Luxembourg. So we started with a project, an Interact project, a greater region, which was called CO2 Redress. And here we tried to find an alternative material, a secondary raw material, as a substitution material for a cement. And so we did an approach where we really tried to identify waste materials which were based on gravel wash muds, so muds which were generated or which are generated when gravels are taken out, excavated out of soil. Then a second type of material was overburden material, so material which was or which is located at the top level of an area which has to be excavated when in order to get to the interesting material. So these were the main materials we were basing our study on in order to see whether we could generate alternative materials. So based on this classified waste materials, so we tried to see whether we could activate, calcinate these materials, which were mainly based on clay. So we were working on calcined clay material, but based on waste as origin. So now we can go to the next slide, where you see a bit our approach in our project, this Interact project of the greater region. We, apart from action 1 and 2, which were dedicated to communication and to management. So you see here the different tasks of the different universities. So we were 4 universities working here together in order to have a common approach and to identify how we could come up with an interesting solution. One has to say that this project was only a 2 years project, so it was a bit limited for our first approach. But with action 1, which was done at the University of Trier, so there were done a mapping of different materials in the greater region area, where we tried to identify and also to quantify the materials that are available as waste materials. And they also started to do a first study on the potential of these materials, on the reactivity of these materials. With this, then we continued at the University of Luxembourg with Sinan Kasamani, so my doctoral student, in order to see how we could develop a process in order to have an optimized process, an optimized calcination process, so an optimized treatment method in order to get the highest reactivity of this calcined clay as possible. So we were working at lab scale at this step. Then there were the University of Lorraine, which were then trying to see how was the potential if they had different additions still added to our waste clay materials, so they did still add some other additions in order to come up and to further increase also the substitution rates which are possible. And then at the University of Liège, there were the study of the environmental impact through the comparison of the life cycle assessment of the different additions that we developed within our project. So this leads me now still to an overview of the full consortium that you see here. So we had a part of the 4 universities that you see on top. We had different producers of materials, of gravels or other materials. We had also like Cariaphyte or Kloos or Carmeuse, Echium, Ahrweiler, Kiesbrandemer, Eifeler Kalksandstein und Quarzwerke, Reich STV. So these were all producers of aggregates, and apart from this, we had also cement producers like CBR, Simalux in Luxembourg, but also Vicar in France. And especially Vicar in France was developing within this project a semi-industrial production line in order to generate calcined clay. But then we have had also producers like Content of concrete elements, which were quite interested in our study, as also Weber from Saint-Gobain. And now I would for now reach over to Sinan, who will give you an insight of the studies that we did at the University of Luxembourg on the different materials which were identified. So, Sinan,
thank you very much. Yes,
take over. Many thanks.
I'll take over from here. Yes, so just to try to explain in a nutshell, how does CO2 Redress as a project contribute towards sustainability? So in a concrete matrix, we are looking at reducing the OPC content, right? So ordinary Portland cement, adding supplementary cementitious materials, so SCMs, and as well using so waste and residual materials. So this is how the project tackled this problem. So we started with the mapping from the University of Trier, who actually they gathered the researchers. They gathered all the materials, more than 35 materials from all the partners that were listed just now. And they did their preliminary studies and selected some samples for further testing that were taken up by the University of Luxembourg and studied in our lab. So first of all, I would just like to remind what was, so the Puzzlanic reaction is something that we were looking for, right, in these materials as substitutions. So we wanted materials with this potential to be able to react with calcium hydroxide and to get more CSH, let's say, into our hardened pastes. So the materials that we studied were 7, even more, but then the ones that we kept until the end of the project were 7. So these were the ones that had potential to be used as SCMs. There were other concepts that were also tried, so such as chemical activation, so geopolymers, and LC3, so with other partners and other universities. But for now, we will just talk about partial substitution of OPC. So with these materials, So here we can see the materials that we worked on. So gravel wash muds and one overburden layer. So this is how they look like. They come from different places in the greater region, and they have so different colors, of course, and different textures. So in the for our experimental outline, in the first step, we prepared these materials. So in order to have better chances at activation of such clays and gravel wash muds, we follow the process of drying and crushing, and then calcination, and then crushing again. So it is of interest, of course, to have a very fine or finest possible as a material as a substitution. So for the activation, as I mentioned, we had a mechanical activation and a thermal activation. So by mechanical activation, we wanted to achieve a better fineness. So we had a drying at 105 degrees for all the materials for 24 hours, and then a crushing at a 2 millimeter sieve. And then we after this crushing, we had the calcination at 3 different temperatures, and then a recrushing and regrinding process. So yeah, these are this was the first flow chart. So by thermal activation, of course, we want to achieve dehydroxylation and then formation of more amorphous phases that are more reactive as well, right? So these are the materials that we used again, but we can see them in their 3 states. So the dried material, and then under it we have the grinded material, and then the calcined material. So you can see the change in texture and in color for almost all of them. And then from now on, like the results that we see are color coded. So everything that's orange would be related to GWM1 and so on. So so for the second step of our project, we evaluated the properties of these materials. So the in natura, right, the pure material, and also the calcined material. So the material characterization, on the material characterization front, we ran tests on dried and crushed and calcined materials. So such as chemical composition, mineralogy, fineness, particle size distribution, TGA, and puzzlenicity as well. I will not show all these results because then it will take too much time. But so it's interesting to, so just to comment what we actually looked for. So for instance, in chemical composition, so we want, of course, materials that are rich in silica, alumina, right? For the mineralogical composition, we wanted to see if so which clay minerals are there? Is it majorly kaolinite, iolite, if there's too much quartz, right? As well with the TGA, so that we can actually measure for thermic gravimetric analysis, where do we have the peaks, right? So exothermal peaks, and where is the dehydroxylation actually happening? And then, so we treated these materials. So first we studied them, and then we treated them thermally, right? So we calcined them at 3 different temperatures, crushed and grinded again. And then we studied again the same set of tests for all of them to see actually the differences. And I will show some in my presentation today. So first, so after studying this, we also made tests on binders and mortars. So to evaluate, of course, strength, compression, as well as tension, but so mainly compression here. So we evaluated binders and mortars for 7, 28, 56, and 90 days with 20% substitution rate. And I will present only the results for 90 days, which I will show later. So for the results, as I mentioned, I will skip the material characterization, and I will get into puzzlenicity. So we studied direct puzzlenicity through Chappelle test and Fertini. So if anyone is not familiar, it's tests that we run. So it's sort of chemical, right? So we're checking the material itself and not its strength. And indirect puzzlenicity, where we are checking the strength actually, so the compression strength of our specimens. After we mixed it, of course, with cement, so as a substitution. So further on, so to move on, the Chappelle test, so I'll just quickly explain it. It's used, so we use the modified Chappelle test. So for 2 grams of calcium oxide and 1 gram of SCM, so the materials that we are studying, and then we measure the total amount of calcium hydroxide or Portlandite that's fixed by the solution. And then so usually there's a line of around 700, the red line that we see here on the graph, and it's the usual value for metakaolins and clays, calcite clays in general. Of course, the commercial ones can be much higher as well. But it's interesting to actually see that many of our materials that were not, so we didn't pick and choose, right? So these are the materials that we had from our partners. So no extra sieving to take out the quartz was done. No, so it's basically trying to actually see the full potential of these materials as they are. So we can compare here the reactivity of uncalcined clays to the calcined ones at the 3 different temperatures, right? So, and then we can see it's an important result because it shows us that the materials are in fact improving their pozzolanicity after calcination at temperatures that are relatively low if we compare them to the temperature of the kilns, right? And then so this is expected to give us reactivity, right? And then we have the Fertini test, which was performed as well for 8 and 15 days. So here I'm presenting only the 15 days results. And so this is a method based on titrations, and it's used to actually determine the amount of dissolved ions, so calcium and hydroxide ions in a solution containing the tested pozzolan. So of course at 20%, so the same amount that we substituted for the OPC. And then we can see the Puzzlanic region is the one that's under the reference curve. And we can see that many of our materials are already pozzolanic at 650 degrees, but then at 750 treatment, as a temperature for treatment, we already have all our materials in the pozzolanic region. And then, so last but not least, so the compression strength, which is, so after analyzing direct pozzolanicity, so we analyzed the indirect effect, right? So through mechanical performance. And here we compare the pastes with 20% substitution rate to a reference, which is 100% OPC, so here. And as we can see, so some of the materials presented lower but higher strengths, but they are almost all of them over the mean of 75%, and even in some cases, some improvements, such as here, 110, 108 for GWM1 and 2 at 750 degrees, also OB1. And so this is for binders, and then also for mortars, we had similar values of around something from 70 to 100%. And as we can see, almost all the materials that we studied are promising. So I give back the stage to Professor Waldman for the conclusions.
Yes, many thanks. So in total, so we were able to identify 34 different secondary waste materials, where 11 of these were promising materials with a high potential to be used in an industrial cement production. Then out of these, so 4 resources showed that they were very interesting in terms of heat treatment combined with an appropriate grinding, so that we really could produce out of these reactive cement additives. Then, so our temperatures, calcination temperatures, were between 650 and 850 degrees. Although we got not a high reduction in compressive strengths, so that we could come up to a high substitution rates, which were about 55%, if we take into account that we consider or we accept a reduction in the mechanical performances of 6% and or 15% for these two materials here, OB8 and gravel wash mud 4. So we could come up with interesting substitution rates. And also another thing is that we tried even to have a combination of different substitutions, so made out of calcine, our calcine clay, and in addition also combined to limestone. So we came up to substitution rates up to 50% without any loss in compression strengths. And it was also then in the life cycle assessment, it was clearly shown that it's the cement which is responsible for the majority of the environmental impact, and all reduction in cement benefits then also in the assessment, in the environmental assessment. So this is then this was a part of this CO2 Redress project. And then I was asked from CEMBUREAU that I could still also present our new initiative. So we are now, and we can go to the next slide, we are now presenting or preparing a new project proposal that we count to submit soon, which is which will also be an Interreg proposal, at this time Northwest Europe, as we do the same, and we use the same approach, but on a larger area. So we want to use waste clay materials and to prepare so these materials as substitutes for cement in order to come up also to a concrete production. So in this new project, which starts already with results of CO2 redress, we also now try to map in this larger area, so of Northwest Europe. We try to find more materials still, and and the difference now to the CO2 redress project is that, as we are aware that these materials are limited in quantities, we will now try to combine these materials locally to blends in order also to have a stability in properties over time. Yes, and to have larger volumes or quantities available, so to come up to an economical, interesting solution. Then in addition, of course, we will do a mechanical and chemical characterization of these materials. We'll do lab tests as well as large scale tests. We want to come up to a full industrial application, full industrial production of waste clay materials which would then be added to cements. So this would be our first product, and in addition, we would also generate other products. Maybe we come back still to the last slide. Sorry, we will come up to. We will try to define other products and make demonstrative projects in real constructions where we have maybe some structural elements realized with concrete containing our calcined waste clay material, and we will also do an economical analysis as well as a life cycle analysis. So in the summary, in the next slide, you see what material we will looking for. We will use gravel wash mud, overburden material as in the CO2 Redress project, but also we will try to have silt material, so from dragging. Then we will do a classification, a calcination test and testing at laboratory level. And then we try to build up some different blends out of the different materials which are interesting. Then we continue. And so in order first to create a new binder, which would then be a cement clinker plus gypsum and calcine clay. And this will then be used. So this new binder will then be used in concrete production and in order to produce a more eco-friendly concrete. And then in the next, so you see the current consortium, which will build up now. So we have different representatives from different universities. So this is representing the research part. You could go on. And then we have a Buildis, a producer, for instance, of prefabricated concrete elements in the Netherlands. We have CEMBUREAU, which is a company which is a partner in the construction sector in France, and which tries to build up economic and environmental friendly concrete elements. Then we have also Dresslabau, which is a concrete producer of structures in Germany. Steffen Schmidt Group will do the mixes. We have the cement producer Vicat as well as Dukerhoff on board. And we have Weber Saint-Gobain, which will now try to use our new concrete in 3D printing in the Netherlands. And we have a producer like Fives Group in France, which are producing flash calcinator in order also to have an impact on this equipment. And then we have some associate partners like CEMBUREAU, Solid Unit and Bauwirtschaft in Germany. Some producers of aggregates, Arweiler Resch, and still Simalux in Luxembourg also as cement producer. So if you found our initiative interesting, then I would maybe encourage you to come and get in contact with us, as we are still a bit looking to build up our consortium. However, our submission deadline will be the 9th of February, so it's not so much time left. I thank you very much for your attention. I am open for your questions.
Thank you very much, Danielle and Jinan. Also, very interesting presentation and a very nice project involving many countries and many universities. There are many questions. I have to say there are 13 open questions, but due to the timing, I will only focus in one, let's say, to answer live. And if it's okay for you, you can answer the rest by typing. And so this is from an anonymous attendee. How did you screen the potential of those 7+ materials? Based, for example, on chemical composition, mineralogy, or reactivity tests like solubility, R3 test. If you could please answer that.
Zinan, you want to ask?
Yeah, I can go. Yes, totally. So in the beginning, we had more than 30, 35, even almost 40 materials, as I mentioned. And then the screening started with the University of Trier as our first partner who got those materials. And then there were indeed so that we looked at the chemical composition together. So if we how much of percentage of those materials were rich in silica, in alumina, and many of them were, many of them weren't. So there was also there were also studies on particle size distribution, for example, which is something that I didn't show, but we had some materials that were on the very coarse side, so we already know that it is not good as a substitute. And then yes, so these are two examples of the criteria that I can that we use that I can give if there's something more that Professor Feldman would like to add.
Maybe what I could add is that in the new project now, we would like to find out a procedure and a simplified procedure in order to identify the most relevant parameters which have to be checked, as we did a very large field of different, a lot of different testing. And however, the relevant things are now more or less clear, so that we could also prepare and hand out how to proceed in order to have really a reduced amount of tests to be done in order to see whether a material has a potential or not.
Okay, thank you very much, and good luck also to the continuation of the project, and we look forward for more results. So thank you very much both, and for the attendees, you please continue this nice interaction with a very active exchange with many questions. So now we can
thank you, Nikos.
You're welcome. Now we can return back to the industry side, to the practical examples from the research, going to the kind of success story from Switzerland, from Holcim. And we'll pass the floor to Arndt. So Arndt is used to work in the Swiss Federal Laboratories, afterwards to the SICA, a big supplier for the cement sector. And since 2021, he is the head of Customer Solutions and Technical Center in Holcim. So Arndt, the floor is yours now to present the topic. Thank you very much. You are on mute.
Hello to all. I'm very pleased to give this presentation on cement using process building rubble. In fact, it's an implemented product containing about 20% of mixed rubble. So just okay. So first, I'm going to introduce the concept.
Sorry to interrupt you.
Yes.
There is a type of echo. Maybe it's another microphone that is open.
No, there's just one mic. Is it okay now?
It is the same.
Okay. Oh, I'm sorry.
If you have headphones, for example, that you could use perhaps, or otherwise, okay, you can continue.
Okay. So then I will take you to the rather successful journey of this volcano, and then referring to some the normative framework, which is very important to have to be able to launch such a product, and then give you some insights or perspective, waste perspective of using waste in as a mineral component in cement. And before summarizing, there were some challenges that we experienced in developing and launching this product. So basically, sustainable is not just a demand, it's a concept, and in fact, it's turning.
And I wanted recording in progress, and I wanted to be a bit playful also with CEMBUREAU. So I wanted to change the title from 2050 to 2030. I would like to see the results of our actions, and from the European cement sector to the global cement sector. And I wanted to make the change also because I think the solutions we create in Europe cannot be extrapolated in other regions of the planet. I don't think that collectively we'll manage to have an impact on the carbon dioxide emissions. More than 50% is, of course, produced in one country. So I think at the end of the day, we should think globally, not just for Europe. So consciously, I put some slides forward with technology that I think it's of high TRL, can make an impact relatively soon. And I'm trying at the end to do kind of, psychoanalysis of why things are not happening, although they seem so good in papers and in presentations. Famous slide by a colleague and a friend, Ruben, you see on the left hand, different SCMs, blast furnace slag, coal combustion and the likes. Some on the more left hand are primary sourced and other residues. Message from that slide, and I think from the quote I took from a paper of Professor Scrivener, is that although the most viable option involves blending cement and creating this blended, of course, cements with SCMs, the availability of these common SCMs is low compared to the demand for cement. Of course, demand being 4.2 or something like that, billion tons globally, indeed, other materials might not be readily available. So I took that and I'm trying to reverse engineering and I'm changing it and I'm putting the question forward in this slide, under what conditions uncommon SCMs can become available in substantial quantities to the cement industry. So then I'm trying to answer each one of these lines, uncommon SCMs, availability, quantities, and of course, how that can help the cement industry in practice, which means really minimizing the CO2 emissions, ultimately the whole environmental impact. Part of the culture here, if something doesn't exist, make it. So what do I mean by uncommon SCMs? People usually associate cements with calcium aluminosilicates. We see differently. We start from thermodynamics, and you see a ternary diagram. So please don't be intimidated. It basically says that if you are, and I hope you see my cursor, if you are in this region or in this region at 1200 degrees that you see here, and that's between calcium, iron, FeO, iron 2, silica, and the 0, 5, 10, 15 is the alumina content, then your mixture is in a molten state. So successfully, you just made the glass. Why do I pick these 4 oxides? Because these are the most abundant oxides. So forget borates, fluorides, and the likes. We want this cement to be available for the whole planet, a democratic cement, as I call it. And we also want to find the minimum in terms of melting temperatures. So not 1450, but in this case, 1200 to make something that is in fact a glass to be. That can be bigger. What you see, in fact, is the non-ferrous metallurgy, and eventually we rediscover the obvious that these glasses are also called slags. When you speak about copper production or lead production, these are the typical chemistries that the industries are working with. But in fact, that can be a bigger story. Then a number of metallurgical industries could convert their residues into these selected chemistries. Now, pay attention in the high temperature process that you are going to be employing. You can also do fuming. Fuming implies that certain metals or elements can simply become volatile, so they will leave your process. So you have, let's call it a heavy metal depleted glass, not science fiction. I can give you examples on that. And of course, you can also selectively choose the way you do your cooling. So you have certain phase precipitating, incorporating heavy metals inside. Spinels are the usual suspects. In case you start asking yourself, where can I find that? Bottom line, you can see a list of alumina refineries. That little thing right corner up is a car to get a feeling of the scale. And of course, this is something that has been in my life for some years, decades to be precise. It's called bauxite residue, also known as red mud. Lots of iron in that context, in that chemistry, that we try to valorize it into products simply because it fits the thermodynamic calculation we've done in the slide before. Speaking of calculations, here is the methodology. So I'm trying to give you guidelines to use yourselves and take it home. You just need thermodynamic software. In this case, this is FactSage. You can do two things. Check of course, the melting temperatures, and then check the viscosity. And besides FactSage, there are other softwares that can also give you viscosity data. In this particular case, you see with the red dot, the starting chemistry, and with the heart, what's the chemistry after the addition. Again, selectively and consciously, we want minor additions. So we want the majority to be the residue. And in this case, silica and calcium are just minor components. You still need some carbon because you need to go from iron 3 to iron 2. Now, of course, we're working also with hydrogen, and this carbon can also be biogenic carbon, so it doesn't necessarily contribute to more CO2 emissions. On the right-hand side, you see thermodynamic equilibrium, but depending on the cooling rate and the glass forming ability of your melt, you might have more of this component, which is important, the amorphous fraction. How would you do that in a bigger scale? We have our own containers, but it's not that difficult after all. You just add your precursor, your residue in this case with the silica and the alumina, and the calcium. You can add the 2% or 4% of carbon. Then it's a filter press at the back. You produce what we're calling in the lab our sausages with the components inside. And then you go to a university nearby in Aachen and you make 5 tons to see if what you say makes any sense. Your slag will look something like that. And then you have to do the milling, and you can use existing infrastructure, being a ball mill or a vertical roller mill, to do it. So we know also about wear rates, throughput, and energy consumption. Please don't be intimidated. It will be fine. What do you do afterwards? Yes, some publicity first to conceptualize the thing. Your mud becomes a black slag. And then you bring together, I think that's the interesting thing, all the non-ferrous metallurgy, both the alumina refineries and the copper and the slags and the lead together to create this black precursor. And you can play them with the words. The red becomes black and the black becomes green. Seeing of performance now, what you can do, 3 options. You can do inorganic polymers. Inorganic polymers is what some people call geopolymer, but geopolymer, the inventor of the word, will have now a hard time because he selectively, carefully says this is aluminosilicate. This is not an aluminosilicate. It has plenty of iron inside, so it's an organic polymer. It's a bigger family of materials where the geopolymer can be actually a subsection of that. If you add a sodium silicate solution, that's the first option. Or you make hybrid cements, a tiny bit of alkalinity. And here you have, in fact, also Portland cement and limestone. Inspiration to some extent has been from LC3 cements, or you can also go to more classical blended cement formulation that you see on the right hand. So 3 options, and per case you have different performance, different impact, different advantages and disadvantages, also different hydration products. So in the first case, you can see here the performance. I think most people will be asking about that. 28 days, more than 100 megapascal, 2 days plus 50, 7 days, about 90. Hybrid cements, depending on your mix design, but anyway, 28 days, still very, very decent. I would say 40 megapascal. In terms of environmental footprint, this is the best, and in terms of cost also. Blended cements, also very good, more than 50 megapascal in 28 days. Usually people are reluctant for the early strength, but I think it's decent, and it can, of course, can be even enhanced, because in the blended cements and the hybrid cements, plasticizers do work. So if you have access to PCs, please give them a try, and you will see that things will go upwards with respect to performance and perhaps with respect to durability. Question, is it really sustainable? And my answer is yes, and the extent depends. And you see here the clinker, and you see here the VBR, or the vitrified bauxite residue. So depending on how you do the reduction, and depending on what is your energy mix, your electricity mix, you have different numbers. What is important is this one, that theoretically that can be 0, because we're not having limestone in the formulation, and we're using electric furnaces to do the job. So if that is really coming from a green source, the power, then indeed that is a precursor that does not have any CO2 emitted. Can we upscale? Yes, we've been doing this for years because nobody was taking us too seriously. So we start with a table and the famous painting, Cécile Pound slag. You have to come to Belgium to discuss that. Then we made tiles, the stairway to heaven, more than 140 megapascal in compressive strength, also with fibers inside, tiles or slate tiles. And the last thing we did this year, or the previous year actually, was a porous panel that can withstand fire. That was done in 2022. It's 180 by 1 meter, and it has been tested also by independent labs in Spain. Believe me, it is good in a thermal shock. So it can put that, you can put that in the tunnel, and that's also an application. Classical also question, where can I find those things, and how can I really meet the demand? My answer to that is there is availability, both in nature and of course in our processes. So when we speak more for valorization, you should see the ladder more from tailings upwards. And the more you go up, the more you have something that actually can be used almost today because it's already vitrified. The more you go down to the left, the more you start going into mining. But we use plenty of iron ore, more than 2 billion tons a year, and there are still reserves around. And in fact, we're not actually going in competition with the iron industry or with the alumina industry that needs bauxite. We are looking into reserves that have high silica, which is not a desirable component in these minerals, in these ores, to be precise. So I think we can still be complementary to others and eventually meet the demand of this maybe one day cement industry. So far so good. Why is not happening? And I'm trying now to also put myself in the difficult position, and here are what I think could be the case. One is the cost. So when it comes to residues, there will be support from the owner, but when it's a primary raw material, there will be higher cost. And sometimes there's a conflict of interest between an industry that is now having a residue and an industry that has also an iron ore. So it's a difficult exercise. And I think also in the future, there will be competition on who is having access to what. What I see as a trend is that the cement industries evolve into materials industries and covering a wider spectrum. And when I see also projects we have here, I see more and more the possibility for joint ventures and some kind of more strategic alliance between the cement industries and the metallurgical industries. So I see that as a trend, and I wanted to put it forward. What about the available quantity? Europe alone, 171 million tons per year. How much can we really substitute? And my answer is that it depends. Depends where you are, depends what the society is looking forward to see as things happening. Different priorities, I guess, in Greece, different in Belgium, different in Germany or in Austria, we had before. So yes, it matters where you are, but in some regions, the impact can really be high. And I'm very, very honest in that. So how do I see we should be moving forward? Perhaps we should find these front runners. in order to inspire also the others. And perhaps we should also accept that one solution for all is not going to be working. The reason is that distance is important. And when you do an LCA analysis, you see that it has a huge impact on the environmental performance and, of course, on the cost. So I think we should be looking in our vicinity, what can we use nearby. Third thing related also to the use of waste, which I find, I hope you find this interesting as an example and to some extent entertaining. Two aspects here. One is the pressure cooker, and why are we so okay in creating performance-based standards on making our food? So we take it seriously that this is not going to explode. It has to sustain a certain steam pressure. But when it comes to cements, we have still prescriptive standards. Philosophical question. The second philosophical question is to the right. If you know about stainless steel, plenty of chromium inside. However, you're not really doubting that this will end up in your food, in your soup. On the other hand, when we speak about alternative raw materials, we refer also to the total content, not only to the leachable content. See presentation before. So also a question to me, why are we doing that to ourselves eventually? And why don't we just also create performance-based standards, which happen to be available in other countries as well as in Europe? And I know durability and risk and fears, fine. What if we start from applications where we can actually live and manage this fear? Another one that I think is very, very important. We care for the environment, I believe that, but at the same time, things happen too fast and happen concurrently. And I think it's difficult to digest what's going on and how we can get away with all this evolution. And to some extent, and I guess that's also part of the human nature, we still think of our business. We cannot always have this overview. And I give you some examples of metallurgy, so you can see that actually they have the same exactly problems and challenges. But my point here is that if we really care about sustainability, energy, metallurgy, and the building materials are all interlinked. I'll give you an example. On the left hand, you see, it was a question so before, the percent of electric arc furnaces in the United States. And if you go back in the previous presentation, the last one was also about percent of, you could use slags from EAF. Now, in 20 years time, this has been basically from 50% all the way up to 70%. Okay, that's in the United States, crude steel production. In Europe, the numbers are different. I think we're to some extent more thinking, what is the way to go? Now check the right slide, and that means that depending on your energy mix and how you will have your feed in the furnace, you will end up with different technologies. And there's a whole evolution now in metallurgy in Europe. What is the best available technology? And big trials are happening in different locations, from Scandinavia to Belgium to Austria and the likes. Now, every single process you choose will have a different impact on the slag quantity and the slag chemistry and mineralogy. And I come to the next slide. Now, how do we really make sure that this is the best overall solution for the environment? Because it might be absolutely perfect for the metallurgy, but collectively as society, this might not be the preferable option. And that's a difficult one because we need to think wider in a symbiotic manner. And of course, that goes beyond the boundaries of my own business. Sadly, of course, CO2 emissions have no motherland, so they affect us all. It doesn't matter if they come from the steel industry or from the cement industry. And the last thing, and then I guess I'm a bit teasing academia or people who know about everything, is that sometimes we think that certain things are true and will remain true because that's what our experience has been telling us. For instance, we've seen in our work that people would think that if you have sodium, you're definitely going to have alkali silica reaction. Iron silicates cannot work. And we did it. We took only iron, oxygen, and silicon, and we made samples out of them. And of course, that is difficult to speak with people from different sectors. They will not understand our language. But I would say that these statements are only occasionally true. In many, many cases, the boundaries are now much more diffused. We all have the same problems, so we'll try to understand each other. And I think we should be more open to that. Hopefully, with AI and machine learning, this acceleration is happening. And I believe that the future cements will be actually a bit more clever than the cements today, more multi-component, including also organic additives, not just binary. So why is that happening? let's flip it around. Let's make it happen. I truly believe the cement industry is an enabler of circular economy, and that can be indeed further intensified. There are technologies available. These are the so-called low-hanging fruit at the TRL more than 6, and that can have an impact on the emissions today. I also believe and support closer collaboration between the cement and metallurgical sector. In fact, also the energy sector, because the problem is way above our league. We should be looking into collective solutions. And I also feel that the boundaries are way more diffuse nowadays than what they used to be in the past. And there is more understanding. That's the nice thing between the different sectors. And yes, it's more than emissions. Thinking of what happens in Ukraine and other regions, I believe that all this collaboration will lead to more co-growth, more industrial symbiosis, or the so-called process for planets, now initiatives by the EU, and ultimately to a more resilient environment for a continuous growth over the years. And the last thing, and I would like to stick to that, we are in this transition together. So I think there is no space or room for blaming. We need each other, and we should be helping each other. And I hope I finish on time. I would like to acknowledge a number of projects over the past years, and I'm really, really open for questions. It has been a very nice chat in the background.
So thank you very much, Yanni. It was a very inspiring presentation, I have to say. Very nice quotes I have noted, like democratic cement, black is the new green, playing with the color of waste and the environment.
I'm a marketing guy also, funny enough, yes.
Very good, yes, excellent. And the closer collaboration as well with the different industries, metallurgical, energy, cement, for the common issue of CO2. Very good messages. I would like to address one question that is in the Q&A related to the, I will read it to you. Based on your expertise, what do you think about the current ambition of the cement industry to reduce the clinker to cement ratio to 65% in 2050? Should it not be much more ambitious? Before giving the floor to you, just to mention that from our CEMBUREAU side, we have an answer to this question in our Q&A that is available on our website, but we're very much interested to hear your perspective as well.
Yeah, it's an interesting question, and I have a difficulty in answering it, not because CEMBUREAU is listening, but because what we often do, and I see that also with the EU policy, we define the targets, we define the ambitions, but we do not define how we will reach those ambitions. So I would like us to focus on getting things done now and collectively, and I think ultimately we will reach this ambition. Speaking for 2050 is hard for me. I don't know if I will be around, and I think to some extent, in a very elegant way, we postpone our liability and responsibility for our kids. So I would like smaller things happening faster. And I think ultimately this will create this self-propagating reaction of innovation, cultural change, and things will happen. But I want to see more the small things. And then it will just, happen by itself organically. We will wake up in 2050, hopefully, and we'll see a better planet.
Thank you very much. It's a very inspiring answer as well, together with your presentation. So if there is also one more in the Q&A, two more, if you could please have a look. Meanwhile, until the last minutes that we have, your presentation together with the others will be shared. Also the recording. So the attendees could be feel free to reach out to the individual speakers also after our webinar. So also, Yanni, if you could please stop sharing your screen.
I want to do that. I don't know how to do it because I only see news. I see now. Jesus. Okay, thanks. Sorry.
Okay, perfect. No problem. So I think now we can go to Mr. Rob van der Meer to give the conclusions of the webinar. And Rob, the floor is yours now, please.
Okay, thank you, Nikos, and thank you all for this very interesting presentations. I drafted a lot of conclusions, but I have limited time, so I have to be very fast and selective. First, I think Volker showed very clearly that, and that's also back to the point of Yannis before, we have, as cement industry, high targets on the use of alternative materials in cement industry, including clinker substitution in cement. And these targets to be achieved in 2030 and beyond in 2050, that will be a huge effort and not easy. On the use of alternative raw materials, the feedback from Volker was that Austria is in Europe a clear benchmark example, but also it is clear that data that is to be used, especially on the use of alternative materials in concrete, is a challenge. We lack information, and I think that is a fundamental issue everywhere in this type of discussion. It is also going back to what Yannis said before, setting targets is beautiful, but how to implement them, how to achieve them is not that, that's more important. What I also learned from Volker are in fact two issues that are perhaps less mentioned in all these discussions. That is societal perspective, the acceptance of raw materials, new processes, new products mentioned by several in this meeting, by the society, by the users of the concrete, by the users of the cement, but also the environment, of course, the people in the neighborhood living and further away. There are also political challenges, and Volker mentioned them too, for the implementation and all that. That brings me to the second presentation, CO2 Redress from Daniela and Sinan. They have looked at seven materials for to use in as a clinker substituting material. And the message that I got from it, it is not simply putting a raw material, an alternative material, just putting it in cement and then it's done. It's much more complicated. You really have to look at all the details. I guess I knew, but I'm now aware again, so thank you. And that in fact, sometimes you need a separate production process to have good materials to be used, even that you start from a material as such that is interesting. What it also shows is that the LCA analysis showed that advantages of these materials, and that is not a surprise, is that the advantages of these materials are high compared to traditional cements. And I think that is, of course, what we all know, but it is nice to see that shown again. And what I especially liked in this presentation at the end was the focus on continued research and development on this type of processes. I don't think that we should stop here. We have really to work all on this, and not only for the next 10 years, but for the next, I guess, 100 years. We are only at the start of all this. Yannis also showed that. The presentation from Bernd Arndt showed really that when you have a beautiful material, it is not that simple to use that material from a legal, from a standardization perspective, and also from a waste legislation perspective. Is it a product? Is it a waste that really has consequences? The question is how to put that in a product portfolio. It was clearly shown that you have an increase of the circular efficiency, or in the circular factor in it, a reduction of CO2, and the use of certificates, CO2 certificates, as a possibility for funding. I think that is interesting from this perspective. But what I really also liked in this perspective, that is the many applications that have been shown where it is used. So it is the concrete rubble where we are talking about is in fact an alternative for scarce raw materials, but it is not that simple. And he mentioned, I think, 3 or 4 key challenges. The first one is the stable and sustainable sourcing of these materials. Yes, and not only of concrete rubble. It is a fundamental issue, I think, in the recycling in the cement industry. It should be stable source and it should be sustainable. There are no technical problems that I understood, no real technical problems. Interesting, and the increase of acceptance starts with the CO2. We all know that, but the circular part is not to be neglected. That brings me to the last one. That was from Yannis about uncommon SCMs. Thank you for that, uncommon SCMs. Massive volumes are available, red mud, copper slag, BOF slag, and others. All these materials deliver, in fact, when you use them in the proper way, a broad portfolio of perhaps green cements. Interesting to see that. But why is it not used? And that was, for me, one of the essential things that is coming out of this this webinar. It's about cost, why it's not used. Cost of these materials, cost of these alternatives are higher than traditional cement. And I understand that. I've seen that in practice quite often. Also, better solutions from an environmental perspective cost money. And do we want that as market? Not always. The availabilities, yes, the global approach is nice, but we have local and regional issues on the availability of materials. The impact can be high and not one solution for all. Thank you, I agree. The missing performance-based standards, yes, thank you. That is a high topic in our business at the moment. The Commission said last year in a communication that they wanted to have performance-based standardization for cement. But when you ask them people, what is a performance-based standard for cement, you do not get an answer. So we all have to think about what does that mean, performance-based standardization. That it has to be changed, that the standardization processes as it is today is not the answer for all questions that we have from a societal perspective is clear. And the last point from the presentation is that, and that brings me back in fact to the whole other three presentations, it is a complex issue. It is not that simple. When it would be simple, we would have done it already. We do it tomorrow. But we have to really look at a wider perspective, much wider. We have to look at multi-component cements. And the current cement types, 3 or 4 components, are relatively simple. The 4-component cements are already complicated, but the earlier cement types were rather simple. And still, we have really to work on that transition where it is absolutely needed. And that was, in fact, for me, the last conclusion, Nikos. Thank you all for this.
Thank you very much, Rob. It was a very good summary of all the presentations and the main points by each speaker. So it's almost 4 o'clock in Belgium. I would like once more to thank all the speakers and the attendees for this last 2 hours. It was great having you here on behalf of CEMBUREAU. So thank you again one more time, and wishing you have a good day and a wonderful week. Thank you very much.
Thank you,
everyone.
Bye-bye. Thank you.
Bye.